Good afternoon, everyone. I hope you're all doing well, and I hope that you found the paper one earlier this week manageable. Let me know in the comments how you found it. Today I'm having a look at what could be content for a paper 2 question or a multiple choice question on the paper 3. So we're having a look at a sort of organic synthesis question whereby we are actually having to choose the correct reagent and condition for one of these 5 steps. Now, what I am going to do, and you might want to pause the video and try this yourself first, is I'm going to go through each of the steps and name the reaction, name the mechanism, and have a think about what reagents we should use, and then we can try and match those up with the 4 options we've got here. Obviously you wouldn't need to do that for this multiple choice question in an exam, but I thought it would be a really good opportunity to also just review some of the organic content with you. So if you want to try and identify what's going on in each step before I reveal all, now's the time to pause. If not, we're going to dive straight in. So for step 1, we've got CH3COCH3, which if you don't like seeing it structurally like that, draw it out as displayed or a more displayed version of that. And what is happening is that is a C double bond O in there, which is then turning into an OH group, and then we've got the CN up there as well. So in terms of what's changing, C double bond O is now becoming an OH and a CN. And that can be a really useful thing to do if you're not sure what a mechanism might be. Try and identify the functional groups before and after, and then think, well, how am I going to have been able to go from a C double bond O to a C single bond OH, and then this CN's appeared as well. We haven't got rid of any atoms, we've only added, and the mechanism for step 1 is nucleophilic addition, which I'm going to simplify to N.A. Now, in terms of reagents, we're going to need the cyanide ion to be our nucleophile. And then once we have broken open the C double bond O to make C single bond O, the lone pair on the oxygen will then attack a H plus from a dilute acid. Now, in the old spec questions, you used to be able to say HCN as a possible reagent for this reaction. You can't anymore because HCN is toxic, so they want you to specify using either potassium cyanide or sodium cyanide, and that would be dissolved in ethanol rather than water, and then we would need to add some sort of acid. So HCN was great other than the fact it was toxic because it had the CN minuses and the H pluses. For kind of both parts of the mechanism. But the other thing with HCN is it's a fairly weak acid, so nice synoptic link. It doesn't dissociate very much, it only partially / slightly dissociates, so actually we didn't get a lot of CN minus and H plus, whereas KCN we get a much greater supply of the CN minus nucleophile, and then we can add an acid to give us the H pluses. So step 1 is wrong because we wouldn't be using HCN anymore because that is toxic for 1 and not a very strong acid for 2. So instead we would want to be using KCN or NaCN, and that would need to be in, they usually want you to say aqueous ethanol, so I'll put that down like that. So that one is clearly not correct for our multiple choice option, but we've obviously gone through the mechanism or the name of the mechanism for that one. So again, what has then changed from the product of step 1 to the outcome of step 2? So we can now see that the OH is disappearing, and we've now got a double bond in between those 2 carbons, so we've got to get rid of the OH and a hydrogen off of that CH3 to then give us the double bond there. So in terms of a mechanism and a reaction type, mechanism is going to be elimination, and the reaction type is dehydration because we are getting rid of water. Water is the molecule we are eliminating. So dehydration would be your answer if it asked for the name of the reaction. Elimination would be your answer if it asked for the name of the mechanism for the dehydration reaction. Now, there are two types of elimination. I know that's slightly confusing. We've got elimination involving an alcohol to an alkene, and we've got elimination where we start with a halogenoalkane and we go to an alkene. And again, the reagents and conditions are different. So the option they've given us for step 2 is potassium hydroxide dissolved in warm water. That would give us some alkene product from an elimination mechanism if we had a halogenoalkane, but that isn't what we need to be using if we have an alcohol that we are trying to dehydrate. So again, B is not the right answer for our multiple choice question. For B, we should be using concentrated sulfuric acid. And the concentrated sulfuric acid will provide the H+ that will first of all protonate the OH to make it OH2 with a positive charge on the oxygen. Second step, that then eliminates. Third step, we take the hydrogen off of this carbon, and then the electrons in the carbon to hydrogen bond form our double bond. So it's not B. Step 3, you'll notice they haven't included, partly because in a 5-step mechanism one of them is going to have to be excluded because there's only 4 options in the multiple choice questions, but also the change in step 3 is from a CN to a Q group, and that is not something that is on our specification. Now, I think I've seen it come up once as a suggest what reaction type might be going on to convert a nitrile into a Q. It was a suggestion, it was only 1 mark, so it was nothing to worry about, but in case it does come up again, 2 things are happening. 1, the CN has a triple bond, and that triple bond has to break. And when we break things, lysis means splitting, so we might be thinking hydrolysis, and also if we've then got to add an O, an O and a H, that might be hydrolysis because we're using water to do that. So the suggestion for step 3 would be hydrolysis if it asks you for it, but that's not an expectation that you know that. Okay. Moving on, therefore, to step 4. In step 4, the difference is we've gone from our carboxylic acid Q group to this COOCH3, which is our ester functional group. So we've gone from a carboxylic acid to an ester. There's only one way that we can do that, and that is via esterification. Now, there's no mechanism that we would need to draw for esterification. We do need to know that it would be a carboxylic acid reacting with an alcohol, and because we've got the ester product shown, we can see what alcohol it would need to be. So the Q group will lose its OH and keep the C double bond O, and then the O and the rest of the alcohol add on to that same carbon that has the C double bond O. So CH3 and an O means that the reagent would need to be methanol, which they've given us. The bit that's wrong with this one is the alkaline catalyst. It wouldn't be an alkaline catalyst, it would be an acidic catalyst, and specifically, again, we would be wanting to be using concentrated sulfuric acid. So almost for option C, right alcohol, wrong catalyst. So concentrated sulfuric acid there. So that means by process of elimination, step 5 has to be the correct answer. In step 5, we are opening back up the double bond that we made earlier, and we're popping a hydrogen onto each carbon that was previously a part of the double bond. So you could do an electrophilic addition mechanism for this, although it's not one, again, that we would usually do. electrophilic addition, the 3 electrophiles would be a halogen, a hydrogen halide or sulfuric acid, but it would work the same with hydrogen. The type of reaction we would call hydrogenation, which if we think about when we're talking about benzene and why benzene is different from cyclohexane-1,3,5-triene, they often give us enthalpy of hydrogenation data, so breaking the double bond, turning it into a single bond by adding hydrogen. Now, again, we don't necessarily need to know about hydrogenation as a process from an alkene to an alkane, but the reagents that we've been given for the H2 with a nickel catalyst, they're the reagents that we use when we're opening up the CN triple bond in a nitrile and turning it into an amine. So breaking open the triple bond, turning it into a single bond and adding hydrogens onto the carbon and the nitrogen. So if we're breaking open a double bond and putting a hydrogen on each carbon, that would suggest that these reagent and catalyst for our condition should work. But also, if we know it's not any of the others, which we would need to know specifically what we would use for those processes, then, like I said, by process of elimination, it has to be D. So there we go. Now, that could be presented as an organic synthetic pathway, and it might be that the question was, part A, outline a mechanism for step 1, name the organic product, and then part B, name the type of reaction for step 2 and give conditions. Step 4, write an equation for the esterification of this becoming obviously the ester. Something like that as part A, B and C. And there could be more than that. So that's why I wanted to go through that. In terms of our multiple choice option, step 5 is the only one that has the correct reagent and condition. So that's our right answer. And if anyone has any questions about either the specific nature of this question with the reagents, please do ask. Or if anyone's got any questions about sort of the more organic synthesis / mechanisms and names of reactions part of what I've answered here, again, please just let me know. Hopefully that's useful, and I wish you all the very best for your paper 2 and paper 3 revision, and there will be more videos pre-paper 2 and hopefully pre-paper 3 to come, so look out for those. Thanks so much for watching, guys. Take care.